Hello. So now we've got sources that we got from the web. We've got sources we got from databases. Let's talk about evaluating which ones are the best ones and also how you're going to actually do your annotations. So I keep talking about peer review. If you are not familiar, peer review is a way people can fact check stuff. People can go through, try to recreate the results of an experiment. They're going to see about looking where the scientists got their data from. Basically, it's looking up where everybody got their stuff. And the fact is, if someone can't reproduce the same results, if someone can't follow the pathway and find things, that's going to be a bit more of a problem. Well, why isn't everything peer-reviewed? A lot of issues, this is why it's so important. I'm going to talk about something rather serious for a moment. Back in the 1970s, Charles Welty diagnosed a cause of death in a group of women as excited delirium brought on by drug overdose. His main citation was something called Bell's mania, which was a study from the 1800s. Thing is, Bell's mania is not a correct diagnosis. William Bell, the man who coined the term, was a psychologist who had a bunch of patients with all different symptoms that he lumped them all in together. So basically, William Bell could not actually diagnose something correctly because his patients were all showing different disorders. He just lumped them all together. Welty, with his excited delirium diagnosis, is actually giving an incorrect cause of death. Here's the thing. Those were not drug overdoses. The women who were diagnosed as dying of excited delirium brought on by a drug overdose, they were murdered. It was a series of murders. But Welty basically cited a source that doesn't work, that does not hold up to academic scrutiny, and as such, justice was not served for the women who died. This is why it's extremely important to look at and study the sources that you are looking at. Here's what's worse. Excited delirium is still something that is cited to this day. It is something that is made up, but you can look it up right here. Sometimes you get something useful, like the AMA saying that excited delirium is not an actual diagnosis. Other times, you've got the Federal Bureau of Investigation talking about excited delirium as a serious medical condition. The FBI, this is a .gov website, as you can see on screen, is literally citing a disease that doesn't exist as a serious medical condition. People still cite this. People still say excited delirium is a thing. One of the most powerful law enforcement agencies in this entire country is citing something that was bunk science from the 70s. Why? Why does this happen? It's not always someone just twirling a mustache. Sometimes it's something like what they call publish or perish. Basically, someone, in order to keep their position and keep their academic career, they need to publish something. They need to have something that is forcibly put out there one way or the other, and they just hope that whatever they do, it doesn't get enough scrutiny to prove it's wrong. Other times you get tricked. There was a scandal a couple years ago about some of the major Alzheimer's research being based on a lie. One study with a bunch of information was falsified. People had used their data and used their model for years and weren't getting anywhere with the research on Alzheimer's. And it turns out that all those people who were trying to research stuff were using falsified data as their model to base everything on. They were basically trying to drive a car, but had no idea their car had no engine in it. All the data was falsified. One of the better websites for this sort of thing is retractionwatch.com. You can go up there and see in real time what papers are retracted. Ideally, there should not be many retractions. In practicality, there are plenty of retractions. There are plenty of times people put stuff out there and it's wrong, or, there are other folks out there who are a bit more malicious about this sort of thing. Folks who have a profit motive. One of the big scandals I remember from a couple years ago involved the MMR vaccine and autism. Coincidentally, Wakefield, the guy who published that article, actually was doing it to advertise a new type of MMR vaccine that he had a financial stake in. So you got to look up also who these people are. But how do we learn how to trust after all this? How do you actually learn how to trust anything? Well, the fact is you got to look at the conclusion. You got to say, does this conclusion actually match the rest of the paper? Because sometimes you'll have a paper where someone is making a conclusion that does not match what their data is. If they can lay out their data and they say, yes, we had a spike in this area, we got to look at it and we got to figure out, okay, does their conclusion discuss that spike in the area? The other thing is you got to compare it with other sources. A lot of times when people are studying things, especially when it's going up for peer review, you got to compare it to other studies in its same field. Look to see if this is a person who's publishing in a legitimate journal, see if this person's actually has repeatable experiments, see if this is a pilot study, because pilot studies are much smaller. They are not necessarily actually definitive studies. They are just a study that is done to say, hey, let's do some more research on this. We can see that there is something here worth researching. Can you look up the author of the publication? That was actually something I did during the Galileo deep dive, but you can actually see sometimes entire careers of people through their publications. Some of those are going to be really interesting, but here's the thing. If you look up someone and their only publications as a scientist are books, not scholarly papers, not peer-reviewed things, there's a problem right there. Because here's the thing, there are a lot of people who can publish a whole lot of books, and if they aren't publishing anything that's peer-reviewed, then those books ain't peer-reviewed either. And then finally, check the methodology. See if it actually passes your smell test. One of the things about Wakefield, famously, was that his entire body of research subjects were in fact kids at his son's birthday party. He literally tried to pass off some kids at a birthday party as a randomized sample for a research paper. Take a look at all those sorts of things. Well, how are you going to check the methods? Well, I mentioned the birthday party thing. That's not a lot of kids. I mean, listen, his kid might have been really popular, but that is not enough to have a decent sample size. Do you have a big enough sample to get good results? And how big is that sample going to be compared to other papers? If you look at other papers in the field and they all are like, oh yeah, we have a sample of 2,000 people, and this paper says, oh, we got a sample of 500, well, that's going to be an issue. And has somebody been able to replicate the methods? Are the methods replicatable? And also, are the results conclusive? What does the statistics actually say? Because someone can say there's something here, but even if something is, say, termed a spike is just an outlier that's slightly different from average. The term you want to look for is significant. In statistics, significance is the term for when something cannot be proven by just random chance. A spike can be just a weird random fluke, but if it's actually significant, that means that even accounting for randomness, this stands out. And finally, let's talk about how they talk about their own paper. When you read stuff on Galileo, look at people's discussion afterwards. Look at the conclusion. They look up stuff called confounding variables. Here's the thing about confounding variables. They are things that every good researcher should discuss. They should discuss stuff that can throw a wrench into their research. Sometimes you'll be looking up something for confounding variables and they'll say, oh yeah, this is an issue because the only people we were able to study happen to be middle upper class. Well, okay, that's going to have a huge impact on the study because there are significant differences if, like, say, you're talking about a study on income. Well, if you only study for middle class people and you don't study anyone below that, that's going to really mess with your income study. Talk about limitations. See what the limitations they say, because a good study knows it has limitations. They say this study can only apply to domestic cats born after 1985 in the northeast of the United States. That is something that is very specific. If they try to make it too general, that's getting weird. That's getting unrealistic. Finally, to make sure some data is significant, look up what statistical tests they did. There's a lot of times where they say they test for significance, that sort of thing. If you've ever heard of something called p-hacking, that is a term specifically about someone messing with their statistical test to make their data look more significant. So go through, you take a look at it and just see, hey, what kind of situation is that? What is the purpose of this study? Are they observing a trend? Are they trying to predict the future? Are they comparing data with each other? Or is it more of a straight up, does this work? All of those things are possible. All those things are things that need to be considered because observing a trend is very different from predicting the future. Observing a trend can be entirely because of just some sort of extenuating circumstance, and you can't use that trend to predict the future. Other times, you can use a model, that is to say, some sort of prediction method, and then compare the model with how things turned out, and that is a way of actually showing a prediction model. Also, you got types of data. Qualitative data discusses the categories of the results. They're basically the way you would describe something rather than using a number. Color, someone saying yes or no. If you put something in a ranked order list, if you say you strongly agree or strongly disagree, that's all qualitative. Those are not numbers. Quantitative is a number. It is a hard and fast number that you can do. Age is a number. Your shoe size is a number. The population, speed, density, weight, these are all types of specific numbers. And a lot of times if you're looking at something that involves, say, environmental chemicals, you might see something listed as parts per million. That is, in fact, a quantitative piece of data. This part's a bit dry, but let me explain it as best I can. Figure out what they're trying to look for. What would be interesting? What would be significant for them? Are they trying to find out if their data is going to give them something that would, say, either be a different range than another data set? If they're looking for something that has a significantly larger number as a result than other things. So, like, for instance, if you're trying to figure out, oh, hey, I wonder if cats born after 1985 in the northeastern United States have a different weight than cats born after 1985 in the rest of the United States. So when you talk about a lot of data, a lot of times you'll see stuff about the center called the mean, median, and mode. Mean is your average. It's just another way of saying average. Median is the middle value, which is not the same thing as an average. If you've got a group of like 5 guys who are all different heights and 4 of them are around 6 feet to 6'1", and there's one guy who is 7 feet tall, the average goes up because it's taking the average of all of those numbers. The middle number, that is to say, if you took all the numbers numbers and put them in a line from most to least, that's a median. So in that case, the median would still be somewhere in the area of around 6 feet because there is just one 7-foot tall guy. And mode, that is the most common result. Mode sometimes comes up in math, but one of the big things with mode is that it's going to come up often enough with stuff where people are doing qualitative situation. Your spread, that's going to be the difference between the top and bottom of your data. So for instance, if I was doing a study on the ratio between your arm length and your height, that's going to have actually a pretty narrow spread because most physical bodies have a same set ratio for that. On the other hand, if I was going to try to rate the amount of money that people win in a casino, well, that spread could be vastly different and vastly wider. And then a model. A model is a fancy way of saying an equation. People make an equation out of this sort of thing so that way they can better predict future results. Like I said, if someone's talking about making a model, they're talking about finding an equation for this. You also got variance. Variance is going to be a discussion of how much something varies from a single value. That arm to height ratio, that's actually going to be a very narrow variance. Standard deviation is the recognition that you can have something differ from the center just by virtue of random chance. And standard error is how off something could be just either by random chance or by accident. Sometimes on these results you can end up with stuff that looks significant but is actually entirely random. The way you study this is you use the p-value. If you set a significance level of 95%, aka your p is less than 0.5, that means you are 95% likely that the data you have is significant. It is 5% that the thing that you're looking at was from random chance. Now, 5% is still a 1 in 20 chance. It's not impossible, but it is really important to recognize that if your p-value is 0.5, that's a lot more important and a lot more sturdy than, say, if your p-value is 1, then that suddenly goes up to being a 10% chance that it's random. And you keep going up. This is what people call p-hacking, and it's a way a lot of times you see these articles try to put out faulty info, is they change the factor by which they consider something significant, so something ends up becoming even more significant or looking like it's even more significant when it could entirely be random chance. Always, always, always make sure the paper is using the word significant.